Today we are here with the Module 3 of the Chapter 2, that is Capacitors. So let's begin this module. First of all, we have the introduction about capacitors and capacitance. What is capacitor and what is capacitance? Let us discuss. So an electronic component that stores the electric charge is called a capacitor, and this ability of storing the charge is called capacitance. Moving ahead, let's talk some more about capacitance. Watch here. When the charge is provided to a conductor, it acquires some potential. Whenever we provide some charge to a conductor, there is a rise in its potential, and higher the charge provided, higher will be the potential acquired by the conductor. So we can say that the charge is directly proportional to the potential, or Q is directly proportional to V. Now, removing the sign of proportionality, we will take a constant, and here the constant is C. This C is called the capacitance of the conductor, alright, where C is a constant called capacitance of the conductor. Now, from the formula Q is equal to CV, we can take the value of C as C is equal to Q upon V. This is the basic expression for the capacitance. With the help of this expression, we will define capacitance. So, if V is equal to 1, means we are taking this V as 1. Then what happens? Then C is equal to Q. Now we will read this to make the definition. So, the charge provided to a conductor for unit rise in potential is equal to the capacitance of the conductor. Watch here. The charge provided for the unit rise in potential is equal to the capacitance. Alright. Its unit is coulomb per volt or farad. Coulomb per volt. Watch here. Q upon V means charge upon potential. The unit becomes coulomb per volt, and this coulomb per volt is also called farad. Moving ahead, we have capacitance of a spherical conductor. Alright, let us consider a spherical conductor. A charge positive Q is provided to that conductor. The radius of the conductor is R. So, the potential acquired by the spherical conductor will be V is equal to 1 upon 4 pi epsilon naught Q upon R. This is the value of the potential, or the expression for the potential, that we have already derived in the previous modules. Alright, now the capacitance will be, with the help of the formula, C is equal to Q upon V. In this formula, we will put the value of V from here. Alright, so we will get this. We have placed the value of V as 1 upon 4 pi epsilon naught Q upon R. Now this Q will be cancelled out by that Q, and this 4 pi epsilon naught into R will come to the numerator to give C is equal to 4 pi epsilon naught into R. This is the expression for the capacitance of a spherical conductor. From here we can see that the capacitance of a spherical conductor depends upon, this is the constant, so it will depend upon R, the radius of the spherical conductor. So the capacitance of a spherical conductor depends upon its radius. It does not depend on any factor, it only depends upon the radius. Since this is a constant, so we can write it like C is directly proportional to R, means the capacitance depends upon the radius of the spherical conductor. Now moving ahead, we will talk about parallel plate capacitor. So what is a parallel plate capacitor? Let's see. Watch here. We have two conducting plates, two parallel plane conducting plates separated by a distance d. This device is called parallel plate capacitor, which is having the ability to store the charge. How will it store the charge? We will discuss here. So we can see that two plain parallel conducting plates separated by a distance form a parallel plate capacitor. Now we will discuss about the capacitance of a parallel plate capacitor without dielectric medium. In the previous modules, we have discussed about the dielectric. Dielectric is an insulator. Dielectric is nothing but the insulating material. So we will, in this case, we will not fill this dielectric between the plates, so because we are discussing without dielectric medium. So in this case, we will take the two parallel plates like this, and between these two plates we will not take any medium, but just air is between them, or there can be vacuum. Right, we will take air or vacuum between the plates. So in this condition, there is no dielectric or any insulating material between these two plates. The plates are separated by a distance d, and each and every plate, both the plates are having the area, the surface area A. Suppose the charge plus Q is provided to this plate, right? This becomes positively charged. Due to the electrostatic induction, this inner side of this plate becomes negatively charged and the outside becomes positively charged. All right, the outside surface becomes positively charged. So where does this positive charge go? This is grounded. This positive charge from the outer side of this plate goes to the earth. All right, we have connected the outer surface of this plate to the earth, so the positive charge is grounded. Now let's remove the connection with the ground and let's do some elaboration. Watch here. The potential difference between the plates, between these plates, what will be the potential difference in the terms of the electric field? Watch here. V is equal to E into D. Where does this come from? We have already derived the relation between the electric field and the potential, which is this. So with the help of this formula, we can take the value of V is equal to E into D. All right. Now, due to this plate, the electric field in the middle will be sigma upon 2 epsilon naught that we have derived in the application of the Gauss's theorem. So due to this plate, positively charged plate, the electric field in the middle will be sigma upon 2 epsilon naught. Due to this plate, the charge is Q, and the electric field for this plate will also be sigma upon 2 epsilon naught. All right, watch here. The electric field due to this charge will be away from the positive charge, means in this direction. Right, the electric field due to this negative charge will be towards the negative charge, means again in this direction. So the direction of both the electric fields is towards positive to negative, so we will add them up. All right, and we have already defined the direction of the electric field, so we will not take the sign of the charge. So sigma upon 2 epsilon naught, sigma upon 2 epsilon naught will be the net electric field between these two plates. So we are taking this as the net electric field here, and this D as it is. All right, this sigma upon 2 epsilon naught and this sigma upon 2 epsilon naught sum up to give 2 times sigma upon 2 epsilon naught. All right, this 2 will be cancelled out by that 2. This 2 will be cancelled out by that 2, and we will get this V is equal to sigma upon epsilon naught into D. We have this value of V. Now watch here. This sigma is the surface charge density. Sigma is the surface charge density, means the charge per unit surface area, or we can say sigma is equal to Q upon A. So put the value of sigma as Q upon A. This sigma, we have placed the value of this sigma as Q upon A, since sigma is equal to Q upon A. Now we have this value of V. With the help of this V, we can calculate the capacitance. Watch here. Take this as equation 1 and apply the formula. The capacitance C is equal to Q upon V. In this formula, we will put the value of V from the equation 1. So put the value. The value of V from the equation 1 is Q upon A epsilon naught into D. Now this Q will be cancelled by that Q, and we will get this A epsilon naught in the numerator, and we will have this C is equal to A epsilon naught upon D. This is the expression for the capacitance of a parallel plate capacitor without dielectric medium. Alright, now what happens when we fill the dielectric material between these two plates? Watch here. The capacitance of a parallel plate capacitor with dielectric medium between the plates. Alright, watch here. We have these two plates of a parallel plate capacitor. The second one is connected to the earth or is grounded. The separation between these two plates is D. The charge provided to each plate is Q. Now let's fill a dielectric between them. Alright. When the dielectric is filled, initially it is having no charge, but due to this positive charge, it becomes negatively charged. Why? Due to the electrostatic induction. And when this is the negatively charged, this will be positively charged, and due to this positively charged, this will be negatively charged, and the outer surface of this plate will be positively charged, and the positive charge will be grounded. Now in this case, we are filling the dielectric partially. Partially means we are not completely filling the gap between these two plates. We are taking the dielectric of a thickness T, which is lesser than the gap between the plates, that is D. T is lesser than D, means we are filling the dielectric in this condition partially. We are filling the dielectric partially, not filling the complete gap. We will fill that completely gap later. Alright, so let's discuss. Take the dielectric constant of this material as K. Now remove the ground. Alright, the electric field in the vacuum or the air. Why air? Because in this region and this region, the electric field will be taken into consideration in the vacuum or in air. So we are taking the electric field in the vacuum or air as E. And within the dielectric medium, the electric field is EM. M stands for material. So within the dielectric material, the electric field is EM, from positive to negative. In this condition, from positive to negative. From here, positive to negative. So we are having two kinds of electric fields, the electric field in vacuum and the electric field in the medium, in the dielectric medium. So the total or the net potential difference in this condition will be given as like this. The potential difference between the plates, this V is equal to E. E means the electric field in the vacuum into the gap of the vacuum. Vacuum is this and this. This gap will be taken as D minus T. Alright, the gap in vacuum or air will be D minus T. Remove this T and we will have this vacuum and this vacuum. So the electric field in vacuum into the gap of the vacuum, which is D minus T, plus we have the electric field in the dielectric material and the gap is T. So the potential difference will be EM into T, electric field into the gap. Right, so the potential difference between the plates will be given as this. This is due to the vacuum, the potential due to the vacuum, and this is the potential due to the dielectric medium. Now put the value of EM as E upon K. Where does this come from? This comes from here, because EM upon E is equal to 1 upon K. Now take this E as common. We will have in the bracket D minus T, this, and T upon K, this. Alright, Now we will put the value of E. This is the E, or the electric field in the vacuum. The electric field in the vacuum is given as like this: sigma upon epsilon naught. This is coming from sigma upon 2 epsilon naught plus sigma upon 2 epsilon naught, which will give sigma upon epsilon naught, that we have already calculated in the previous derivation. All right, so we are taking directly here sigma upon epsilon naught. The electric field in the vacuum is sigma upon epsilon naught, that we have already calculated in the previous derivation. All right, now this sigma is the surface charge density. Sigma is the surface charge density. We can put the value of sigma as Q upon A. Put the value of sigma as Q upon A. Why? Because sigma is equal to Q upon A. Sigma is surface charge density, the charge per unit surface area, or Q upon A. Now we have the value of electric potential difference in case of a capacitance of the parallel plate capacitor. In case of the capacitance of the parallel plate capacitor, now we will calculate the value of C, the capacitance. Take this as equation 1 and apply the formula for the capacitance. C is equal to Q upon V. We will put the value of V from the equation 1. So put the value from equation 1. When we put the value of V, which is Q upon A epsilon naught D minus T plus T upon K. This Q will be cancelled out by that Q, and this A epsilon naught will come to the numerator to give C is equal to A epsilon naught upon D minus T plus T upon K. This is the expression for the capacitance of a parallel plate capacitor with dielectric medium between the plates when the dielectric is filled partially. The dielectric is filled partially, or we can say the dielectric of thickness T is filled between the plates where T is lesser than D. Now what happens if we are filling this gap completely? If we will fill this gap completely, or we can say we will take the dielectric of the width D. In that condition, T will be equal to D. Watch here. Here, this width, the width D, the dielectric of width D is filled between the plates. Then what happens? If the dielectric of thickness D is filled between the plates, then T is equal to D. The thickness of the dielectric material is equal to the gap between the plates. So put the value T is equal to D in the previous expression. So it becomes like this. Put the value of T as D. Here put the value of T as D. So this D minus D becomes 0, and we get A epsilon naught upon D upon K. This K comes to the numerator, and we have C is equal to Ka epsilon naught upon D. This is the expression for the capacitance of a parallel plate capacitor when the dielectric is filling the gap between the plates completely. Alright, now let's talk about the symbol of the capacitor. This is the symbol of the capacitor. Two parallel lines like this, and this is the connection. Alright, this is the symbol of the capacitor, and C is representing the capacitance of the capacitor. So that's all for now. See you again. Thank you.